All right, so I want to talk a little bit about springs and the way of looking at them either through work or energy. So we know that the force of a spring is negative kx. Now, some of you have been a little confused about the minus sign. The minus sign here really just tells us that the force is always bringing you back to zero. So x equals 0 is where the spring is relaxed. So if I have the spring extended, so if I call this the positive x direction, if I have the spring extended in the positive x direction, well then the spring's going to apply a force back towards 0, which would be negative in this case. And if I have the spring compressed in the negative x direction, then the force is going to be positive. So, if you're thinking about drawing force diagrams, it's the same rule as always, is you draw your arrows and then the minus signs kind of take care of themselves as long as you're consistent. And the spring constant K is always positive. Now, if we're looking at the work done by a spring, so let's say that we start, we have some object out here and we have the spring extended. And we want to say we go from here, so we call this, x initial, and then it's going to go past 0 to some x final. Well, if I want to say, I could kind of break this up into two parts, right? What's the work done by the spring as we go to x equals 0, and then what's the work done by the spring as we go from x final. So in this case, when we let go, the force of the spring is going to be to the left, and the displacement is going to be to the left. So since they're in the same direction, that means that the work is going to be positive, and we know that our expression for the work done by the spring in this part is going to be 1/2 kx initial squared. Right, so we get the work done by the spring from here to here is going to be positive. So then if we wanted to say how fast is the block going when it gets to x equals 0, well then we could just say the work done by the spring has changed the kinetic energy. So we could set that equal to 1/2 mv squared and solve, assuming that we know the mass and the kinetic energy, or the spring constant. So then as we go from here to here, the displacement is in this direction, but the force is in the other direction. So that tells us that the work done by the spring is going to be negative. Right, so if we're trying to find, if we start at some x initial and we let it go, so we do some positive work, get some kinetic energy. If we want to see how far the maximum compression is, well then all of that kinetic energy has to go to 0. So we have that the change in kinetic energy is equal to the total work done by the spring, since that's the only force acting on the object in this example. So the change in kinetic energy, well, we started at 0 velocity and we end at 0 velocity, so that's going to be 0. So the total work done by the spring is going to be 0. So that tells us that, so we have 1/2 kxi squared as the positive work, and then we have a negative work, negative 1/2 kxf squared, and that has to equal to 0. So we get that x final needs to have the same magnitude as x initial. So basically, this is going to be symmetric. However far I pulled it out to the right is how far it's going to get to the left. And then the whole process starts over again, left to right to left. Now I could also do this in terms of potential energy. And in this case, I just say that the potential energy here, let me erase. So the potential energy for the spring is always positive, because the potential energy is given by 1/2 kxi squared. So we go from a point where we have this kinetic or initial potential energy, then we get some kinetic energy in between, and then at the end we get the same spring potential energy. So again, it shows us that we should end up with 1/2 kxf squared as our final. So here's US1, here's US2. These have to be equal, and so the starting and final displacements have equal magnitude.